In this video, we're going to work on first order differential equations with integrating factors. Now, this differential equation looks like the following form. It has a y prime, it has a function of x times y, and it's another function of x on the other side. So, for example, I might have y prime plus xy equals sine of x, or y prime plus e to the x y is equal to arctan of x plus x. So what characterizes this sort of problem is that I have one y prime and I have one y. And I have functions of x in these particular places right here. So non-examples are of the form prime plus y squared equals cosine of x squared, right? This is a y square. That is a non-example. Here's another non-example, sine of y prime plus 3e to the x times y equals 1, right? I cannot have a sine of y prime. I can only have a y prime here. Now, that having been said, suppose I have something like xy prime plus 3x. Well, let's do something a little bit more carefully. Suppose I have something like this plus xy equals 3. Okay, notice that I do have an x squared plus 1 in front of the y prime, so the form is not quite right. But I can divide by x squared plus 1, and I obtain the following: x squared plus 1, y equals 3 over x squared plus 1, and this form is okay. So if you can manipulate the equation so that you have something of this particular form, then that still counts. So let's take a look at an example and figure out how to do a problem like this. Let's consider y prime plus 2y equals x e to the minus 2x. Right. So here's a trick. The trick is to multiply by what is called an integrating factor. And what is the integrating factor? Sometimes we call it mu. This function mu is achieved in the following way. You take a look at this object right here in front of the y. Here, the object in front of the y is 2. So in our above rendition right here, this p of x is equal to 2. And so what I want to do is I want to consider the following: e to the integral of p of x dx. And this is e to the integral of 2x dx, which is e to the 2x. And what I'm going to do is I'm going to multiply by the whole thing, the whole equation by e to the 2x. So I have that times e to the 2x, y equals x e to the minus 2x, e to the 2x. These cancel. So I have e to the 2x times y prime plus 2 e to the 2x, y equals x. Now, it seems like we just made the problem more complicated, but in fact, what's really interesting here is the following. Let's consider y to be f. So here's f prime. And let's consider that to be g. Well, this guy right here is g prime. So if you think about it for a moment, this is exactly the result that you get when you multiply fg and then you take the derivative. So this is actually the result of an integration by product rule. Sorry, a product rule differentiation of product rule. So what we're going to do is we're going to go backwards, and instead of writing this guy right here, we're going to write it like this. So this guy is f times g. Well, what is f? F is y, and g is e to the 2x. So this is actually the derivative of y e to the 2x. And I can write it like this. So what I've done is I've taken this object right here, which contains a y prime and a y. So I have two instances of y, and I've reduced it down to one instance of y by using a reverse product rule. So essentially, we're doing a reverse product rule. And now this thing becomes a lot simpler. I can take the integral of both sides, y e to the 2x prime dx equals the integral of x dx. Now, when I take the integral of a derivative, I get the function back. So the integral and the derivative cancel each other out. And then here I integrate, but remember I need a plus c on this side. I also have a plus c on this side. So effectively it's c1 and c2, but then I can move the c1 over here. And then I only really need to take the constant on one side. And now what I want to do is I want to multiply both sides by e to the minus 2x to solve for y. So this is my final answer. So again, what happened here is that by multiplying by this so-called integrating factor, I'm able momentarily to make this side more complicated, but you see that it all reduces down to something actually quite simple by the reverse product rule. Let's work through another example. Consider the equation y prime plus 2x over 1 plus x squared y equals 1. Now let's set p equal to sort of the coefficient of y, 2x over 1 plus x squared. And let's just note that the integral of p of x dx is the integral of 2x over 1 plus x squared dx. And you can do a u substitution. U equals 1 plus x squared, du equals 2x dx. I arrive at 1 over u du, which is an ln of u. And ln of u is going to be ln of 1 plus x squared. So my integrating factor is u of x is equal to e to the integral of p of x dx. And the integral of p of x dx is ln of 1 plus x squared. So the e and the log cancel out, and my integrating factor is 1 plus x squared. So let's multiply through by my integrating factor. Multiply through by 1 plus x squared. So I have a 1 plus x squared y prime plus, and then the 1 plus x squared cancels out with this term right here. I have a 2xy equals 1 plus x squared. Now let's just take stock. This is, let's call this f. Let's call this g. Here's f prime. Here's g prime. And then so this is the result of a product rule. So we can contract all of this to f, which is the y, times the g, which is a 1 plus x squared. And this gets differentiated, and that's equal to 1 plus x squared. Let's integrate both sides. Y 1 plus x squared prime dx is equal to the integral of 1 plus x squared dx. All right, when you take the integral of a derivative, they cancel out. And so you have y times 1 plus x squared equals x plus x cubed over 3 plus c. Now notice that this must be done right here. The plus c must be introduced immediately upon integration. Don't do it later. Upon integration. All right, otherwise you get the wrong answer. And now I'm going to solve for y by dividing by 1 plus x squared. So I just simply get x cubed over 3 plus c divide by 1 plus x squared. And that's the answer. Let's do another exercise with a trigonometric function and some integration by parts. Here I have a y prime plus cotangent of x times y is equal to x. Now here, p of x is equal to cotangent of x. And we can write mu of x, the integrating factor, is e to the integral of cotangent of x dx. Now the antiderivative of cotangent is the ln of sine x. And so once the e and the log cancel each other out, I just get sine x. So let's multiply through by sine x. I have sine x times y prime plus sine x times cotangent of x times y equals x times sine x. Now, notice that cotangent is just cosine of x over sine of x. So this sign cancels out with that sign. And I get sine of x times y prime plus cosine of x times y is equal to x sine x. Let's just double check. This guy is f. Here's f prime. Here's g. And here's g prime. This is the result of doing a product rule. So let's do reverse product rule. F times g is y times sine of x prime equals x sine x. So now let's integrate both sides. Dx. When we integrate a derivative, then my derivative and integral both cancel out. And let's just remember how to do integration by parts. I mean, here's a trick. So you take x and you take sine x, right? And then you differentiate this until you get 0. And then you anti-differentiate this until you reach the very bottom of this chart. And then you look at these diagonals, and then you have a plus here and you have a minus here. So the first term is an x times minus cosine of x. And then you have a minus, right, because of this minus, 1 times minus sine x plus c. Now that's a quick way of doing integration by parts. So I have y sine of x equals minus x cosine of x plus sine of x plus c. So let's divide by sine. Y equals minus x cosine of x over sine x plus sine x over sine x plus c over sine x. So my final answer is a minus x cotangent of x plus 1 plus c times cosecant of x. And that's the end of the problem. Now let's do a problem with an initial condition. So I have, let's try y prime plus 2xy equals x with y of 0 equals 4. So here I have my p of x is equal to 2x. My integrating factor is e to the integral of p of x dx, which is the integral of 2x dx, which is e to the x squared. So let's multiply through e to the x squared times y prime plus 2x e to the x squared y equals x e to the x squared. So again, here's my f prime, here's my g prime. So I have f times g quantity prime, f times g quantity prime, like this is x e to the x squared. Let's integrate both sides. Y e to the x squared prime dx is equal to integral of x e to the x squared dx. And so on the left side, the integral and the derivative cancel each other out. And on the right side, I have a u substitution. U equals x squared, du equals 2x dx. So I have a 1/2 e to the x squared plus c. And let's multiply through by e to the minus x squared. Right, so I have to multiply through by e to the minus x squared, 1/2 e to the x squared plus c. So y is equal to 1/2 plus c e to the minus x squared. Now I have an initial condition when y is equal to 4. Y is equal to 4 when x is equal to 0. So let's plug in 4 equals 1/2 plus c e to the 0. And so that gives me a 7/2 equals c. Therefore, let's go back to this equation right here. So the solution is y equals 1/2 plus 7/2 e to the minus x squared. Let's consider another problem with an initial value. Let's consider y prime plus 1/x times y equals x squared, with y of 1 equals 4. Here I have p of x is 1/x. So the integrating factor is e to the integral of p of x dx, which is e to the integral of 1/x dx. This is e to the ln of x, which is just simply x. The e and the log cancel each other out. So let's multiply through by x. I get xy prime plus x times 1/xy equals x cubed. These cancel out. So I get x squared, x times y prime plus y is equal to x cubed. Now remember that the thing that we're taking the derivative of is y times the integrating factor. So y times the integrating factor is y times x, and that's equal to x cubed. Let's integrate both sides. Yx prime dx is equal to x cubed dx. The integral and the derivative cancel each other out. Yx is equal to 1/4 x to the 4th plus c. Now, so what is y? Y is equal to 1/4 divided by x is x cubed plus c over x. Let's look at our initial condition. Y is equal to 4 when x is equal to 1. So I have a 4 equals 1/4 plus c. So c is equal to 15/4. So let's go back to this equation. I have y equals 1/4 x to the 3rd plus 15/4x. So far, we've been doing problems using indefinite integrals. Let me show you how to do a problem with a definite integral. So in this case, let's take a look at the following. Y prime plus 2y equals x with y of 0 equals 3. Now here, p of x is equal to 2. So mu of x is e to the integral of 2 dx, which is just e to the 2x. Let's multiply through by e to the 2x, y prime, plus 2 e to the 2x, y is equal to x e to the 2x. So this collapses to y e to the 2x prime is equal to x e to the 2x. Now, what I want to do now is I want to do the following. I want to integrate from my initial x0. What is my initial x0 is equal to 0, right? Here's my initial x0, all right, to the variable x. So I'm interested in integrating from x0 to x, x0 to x, but I don't want an x here and an x here. So what I want to do is I want to change this problem to just replace x with t, okay? And in addition, I want to be a little bit careful. So let's replace x with t e to the 2t, and then I have here e to the 2t. Now, instead of y, just plain old y, I'm going to write of t, okay, y of t. So now I'm going to integrate both sides from x0 to x, y of t e to the 2t prime dt equals the integral from x0 to x of t e to the 2t dt. Now let's see what happens here. When I take the integral of a derivative, they cancel out, so I get y of t equals, well, let me just first mention that since x0 is 0, let's rewrite this as the integral from 0 to x of y of t e to the 2t prime dt equals the integral from 0 to x of t e to the 2t times dt. When I take the derivative, the integral of the derivative, they cancel. So I get this from 0 to x. And let's just remind ourselves how to integrate by parts here. I have this little table I can make. So I'm going to keep differentiating the left side until I get 0. I'm going to keep anti-differentiating the right side until I get to the 0 row. And then I have these diagonals. I have a plus, I have a minus. So let's take a look at the first diagonal. It's t times 1/2 e to the 2t, and then minus 1 times 1/4 e to the 2t, evaluated from 0 to x. All right, let's plug this in. Y of x e to the 2x minus y of 0 e to the 0. Let's plug in an x, 1/2 x e to the 2x minus 1/4 e to the 2x. Now, when I stick in the 0 to t, this guy becomes 0. So I just get this term right here. When I plug in a 0, I just get a negative 1/4. So y of x e to the 2x. Now, what is y of 0? Y of 0 is equal to 3. So y of 0 is equal to 3, and that's just e to the 0 is just 1, equals 1/2 x e to the 2x minus 1/4 e to the 2x plus 1/4. Now I'm going to add 3, e to the 2x equals 1/2 x e to the 2x minus 1/4 e to the 2x. So I'm adding 12/4. So I get a 13/4. And then I multiply by e to the minus 2x. Y of x equals e to the minus 2x times this expression right here. And then I can multiply through. I get 1/2 x minus 1/4 plus 13/4 e to the minus 2x. So that's how you do this problem with a definite integral. Let's do another example using trigonometric functions. Let's say y prime plus tangent of x, y equals cosine of x with y of 0 equals 1. Here, x of 0 equals 0. We're going to need that in a sec. P of x is tangent of x. The integrating factor is e to the integral of tangent of x dx. The antiderivative of tangent x is ln of secant of x. So e and the log cancel out, so the integrating factor is just secant of x. Let's multiply through by secant of x. So I get secant of x times y prime, secant of x tangent of x times y equals cosine of x times secant of x. Now this guy is just 1. And notice here, very nice, this is f prime. Here's g, and the derivative of secant x is secant x plus tangent x, which is sitting right here. So this entire thing collapses to y times the integrating factor, secant of x prime equals 1. Now, as we did before, let's change all my x's to t's. Remember to instead of y, I want y of t, secant of t prime equals 1. And now let's anti-differentiate from my initial condition, which is x equals 0, up to x of y of t secant of t all prime dt equals 1 dt from 0 to x. The integral and the derivative cancel each other out. Y of t secant of t from 0 to x is equal to t evaluated from 0 to x. So I have y of x secant of x minus y of 0 secant of 0. Now secant of 0 is just 1. So this is an x minus 0 right here. Now let's remind ourselves y of 0 was equal to 1 here. So y of 0 is, we have y of x secant of x. This is all going to be equal to 1 times 1, it's just 1. And here I have an x. Y of x is equal times secant of x is equal to x plus 1. So let's multiply through by cosine. Multiply by cosine of x. So that kills the secant of x. Y of x is equal to x plus 1 times cosine of x. And that gives us the final answer.